This is Mark. In the previous video, I showed how to relate prime numbers with this set of linear equations. For this video, I'm going to show how to derive the set of infinitely many non-prime numbers that are divisible by a non-prime factor greater than 5. This algorithm it's based on the Goldbach conjecture. During my undergraduate studies, I tried solving it to no avail. Of course, it's been the greatest mathematicians currently are trying to solve it. It hasn't been solved in 400 years, so it's a difficult, very difficult problem. But in terms of the definition or the actual proof, it's quite straightforward. Basically, it states that if you take any prime number, if you take the sum of any prime number greater than 5, like if you take 2 or greater than 4, so any two not prime numbers that are greater than 4 in any given combination, basically it states that you get the set of all even numbers. So I'll mention or I'll explain it more thoroughly later, but here we will utilize the two linear equations. So all prime numbers, we know all prime numbers follow the form. So we have px with index x is 6x plus 1, or py with index y is 6y plus 5. So for this we're going to just utilize this linear equation. Basically, the logic follows the same reasoning, so it'd be redundant to do it twice. And the only difference between these two equations is the constant. So they both have the same slope, but you're adding a constant 1 here and adding a constant 5, for this equation. So if we were to actually plot this on the p-axis, and this is x, what we find is start here, so this is 7, 1, something like this. So basically we're going to have all the prime numbers or the non-prime numbers are on this line, or we also have the other linear equation right here. It's going to be essentially, if we constrain this to, or y is just x, so if we just let them plot on the same number line, so we'd have 1, start right here. So basically these are parallel linear lines, and all the prime or non-prime numbers reside on these two linear lines, using these two linear equations. But basically, if we use a number line, for instance, we're going to utilize px, and we start with the minimum value. If we input, well, of course we could start with 1, but if we input x equals 1, we get 7. So if we start with 7, and then we continue the process, we notice that the distance between these two are going to be 6, 6, so forth. So right here we're going to have 13, that's prime, 19 prime, and then we hit 25, which is not prime. So the logic here, as you start, we notice we hit, so if we started with start with 7, and we hit 25. So basically the key here is, if we were to go, if you say, what if you were to add 6 in one direction, a multiple of 6, let's say we add 6z minus 6z, we add plus 6z to 25. So anytime, we're going in one direction or the other, we're adding a difference of 0. So the key with the Goldbach conjecture is, if you add, like, let's say we take 25 plus 25, so we're taking they're the same term. But essentially what we're doing is, like, we could add px plus px, or we could add px plus p, let's say theta, where theta is not equal to x. So these are distinct numbers, or distinct indices, and essentially, well, we're trying to find an even number. But in this case, we just did this scenario, 25 by 25 px, for instance, p4 plus p4. This is P4 plus P4. And what we get is 50, which is just 2 times 25. It's an even number. And what we notice is, now if we're taking this number line, so we start at 25, we're going to go down now 6, so we hit 19. And we go 6 in the other direction, we hit 31. We notice that, of course, 31 plus 19 is also 50, because we're adding, you add 25 plus 6 plus 25 minus 6. Well, this is equal to 25 plus 25 plus 6 minus 6. So you're just adding 0, and we get the same number right here. But we hit a so we start with the non-prime, and we hit a prime number on either side. So that's what the algorithm, based on the algorithm, you want that. Essentially, the key is this proof fails if you go all the way. So if you're hitting, let's say on the number line you have 0, you're going towards infinity. We hit a very large number, so we're going to go in this direction, 6z times minus 6, and then we're going to go in this direction. We're going to add 6z. After iteration after iteration, z1, z2, z3. So this would be like z1. Let's say we didn't hit it. Z2, we didn't hit it. We keep going, we didn't hit it. And then we go in this direction as well. So we target 3 times, we didn't hit it. We may hit it here and check, but if we hit it here and we don't hit it here, it still fails. So based on the algorithm, if we have an X here and we have a check, that equals an X, a failure. So basically you have to keep going. Let's say we hit it again, we hit check, which is actually less likely going towards infinity. I'm just going to hit it. It's more likely going this direction. Because the larger you go, as you go towards infinity, the separation between primes becomes larger and larger, and therefore the probability approaches 0. So that is a problem. That's why it becomes very difficult. Let's just say this one's check. So then you check, you check both ways. So we have check, check, and therefore this equals a check. So you keep testing, in both directions, and eventually, if this is satisfied for all cases, then a proof holds true. But it's very hard to generalize in this form, so I kind of wanted to find the set of non-prime numbers and relate it to the indices x. And the reason for that is, we know that if we take we have the set of prime non-primes. This resides in the set. So basically this is we have 6x plus 1 such that x is is greater than or equal to 0. And then we have plus, we could just take 6y plus 5 such that y, we're adding all the elements from both of these sets into here. So for instance, we already checked, 6 times 1 plus 1 is 7, so 7 goes in here. 6 times 1 plus 5 is 13, 13 goes in here. And we add basically all the prime and non-prime numbers. But what if you take this set and you subtract non-primes? So we're subtracting that. Well, we're gonna end up getting the set of primes. So basically, if you take the set of prime plus non-prime, and you exclude the set of non-prime numbers, you end up getting the set of prime. And then somehow relating this and trying to get, to the, through exclusion, try to solve the proof, but ultimately didn't get anywhere other than the algorithm. So to start with this algorithm, we start with p of x equal to 6x plus 1.
Now what we wanted to do was relate this coefficient to a variable. So you could say let a plus b equals 6, where a is a divisor greater than or equal to 5. The reason I chose greater than or equal to 5 because for the proof it's dealing with prime numbers greater than 4, and essentially this satisfied that relation. But there's another key piece of information. So if we're relating a as a divisor, so if a divides px, so this means divides, then it follows that px equals to a times, let's just call beta, for some beta in the set of natural numbers. What this means is within the set of, or resides in the set or is an element of the set of natural numbers. So these are all elements. So beta, the set of natural numbers is 1, 2, 3. So what this means towards infinity is beta could be 1, beta could be 2, beta could be 3, and so forth. And what this means is, like, if we take, let's say 12 for instance, we know 12 is 3 times 4, and we know that 3 divides 12, because another way of saying 3 divides 12 is, we know that if you take 12 and you dividing both sides by 3, you divide both sides over here by 3, you end up getting 4. So that's critical. It equals a coefficient. It's like, this is like a beta, but we're not dealing with an even number, of course, like p of x, like kind of analogous to this form. And that's just showing it has to follow. This is a general form. So basically, instead of relating just one number, we're relating a general form, or in multiple cases. So now we know that p of x is 6x plus 1. We know now equals a plus b x plus 1, which we know is equal to a beta. And we know that this is ax plus bx plus 1, so I just use distributive property. So this implies, and then what we can do here is you bring ax over here, and so therefore anytime you do this, you take a positive, ax is positive value, and you convert it to a negative. So by subtracting ax from both sides, we end up getting bx plus 1 equals to a beta minus ax, which we have a common coefficient right here. So it's beta, a beta minus x. Now notice that the key here is, by relating this, so the key here is we know bx plus 1 equals to a beta minus x. So therefore we know that the critical thing here is this is a multiple of a. So essentially we can constrain this beta minus x and represent it as a new variable, essentially condensing it, because it's we wanted to. Okay, so although it is a function of x, it's also, we can represent this as just one variable. So we could just say let beta minus x, a new variable alpha. So therefore we have bx plus 1 equals to A alpha. And therefore, we have Bx equals to A alpha minus 1. And that implies we want to relate this to x. So the indices x. So essentially what we can do now is divide both sides by b. So we have x equals to A alpha minus 1 over b. Now the key here is we notice that if A is less than or equal to 6, B is greater than 0. Because essentially, like, A is going to be greater than or equal to 5, so we could have A is 6, that means B is 0, so A is greater than or equal to 0. And if A is 5, B is 1, so B is positive. But if A is greater than 6, we know B is less than 0. So using this form, if B is positive, of course A alpha plus 1, we know A is positive. This is going to be only subtracting 1, going to be positive. But the problem now occurs when B is less than 0, because as A gets larger and larger and larger, so we start with like A is over here. Well, the distance back into 6 is represented by B, but it's going in the negative direction. So what this means is, like, now we're going to look at A alpha plus 1. So represented by 0, you know, the x has to be positive. So the key here is we know x is greater than 0 for all x. So if b is less than 0, we know A alpha has to be less than 0. I mean, it holds true. So like if we have A alpha, and then this is going to be 1. So this point right here is A alpha minus 1. So this whole distance right here is this A alpha in the negative direction. And then using being symmetric on both sides, this will be negative A alpha, and this would be 1. So given that, this is 1 minus A alpha, or this is also equal to the absolute value of A alpha minus 1. So essentially, if this is a negative value, because A is positive, that means alpha must be, it would be a negative. This becomes negative alpha, it gets flipped over, symmetric across, so it's a mirror image, point right here, and then you just add 1. So it would be, negative A alpha plus 1. So we can basically say so that means x equals 1 minus over absolute value b, because b has to be positive, and that has to be positive. So essentially, or we could just do this equal to absolute value of A alpha plus 1 over absolute value of b. Either or. But basically, now what we notice is, what if we take x plus a? So x plus a, we know, is going to be 1 minus A alpha over absolute value b plus a. So now we break it, cross multiply, so you get 1 minus A alpha over absolute value b plus A absolute value b over absolute value b. Of course, we're just continuing to add a. Of course, so in this case, if we generalize this and we do like x plus a times n, we just have 1 minus A alpha plus a times n, where n is a natural number, which is this n could be 1, 2, and any value. So the key here is once we find the initial point, the initial value, x, we just continue adding multiples of a and that gives us the remaining infinite set. So basically we have x is an element of, it's going to be 1 minus a alpha over absolute value b plus a n, such that we know n is a natural number, and alpha is going to actually be the minimum of, we could just do a variable z such that 1 minus a alpha over absolute value b is a natural number. So what this all means is, essentially, we know that this is a natural number or a rational number. Is a rational number or fraction. We know x is a natural number. And we know that the natural number, if n's a natural number, is a subset of rational number. So basically, if we have a set right here, this is the set of natural numbers, this is a set of rational numbers, and essentially like this is like 1 over 1, 3 over 1, it's 3, but we also have 1/2, which is not a whole number, 3 over 2. So basically, we need to target, the smaller, like we need to continue or find alpha once we find a and b such that this is a natural number and that satisfies the minimum. And then from there, since we know a, we just multiply by a multiple of n, or multiple of a. A times 1, a times 2, and we have an infinite set. So to show how this algorithm works, let's suppose, let's just let a be 11. So we know a plus b equals 6. So 11 plus b equals 6. So that means b equals 6 minus 11 is negative 5. So the absolute value of b, which is absolute value of negative 5, equals a positive 5. So that's the key there. And so we know x, let's just start with the first one. We know that x is a 1 minus a alpha Okay, so we know that's 11 alpha. And so basically right here, what we could have done is, if alpha is less than 0, like this case we're letting alpha less than 0, this has to be a positive value. But what we could do is, because this is like stating like the negative integers. So if alpha, then this is the form. Then we know x equals 1 minus 11 alpha over absolute value b. But if we constrain alpha to greater than 0, we could just state x equals screwed up, damn it. Okay, so that's where I screwed up. Okay. So we're relating this to, yeah, a positive value right here. So, of course, this is like, we can just say x equals 2. And essentially, um, it's equivalent. These are equivalent. Because all we did was, it doesn't matter if they're equivalent, because this is just the absolute value. If alpha is less than 0, then we're representing this as an absolute value function. But it's equivalent if we constrain alpha to be greater than 0, then this form follows. So basically these two forms are equivalent, but this is a condition. So these are the condition. So assuming alpha is positive, this has to be the minimum. So we know alpha is just the minimum z such that 11 alpha plus 1 over b is 5 is a whole number. So this is like trial and error. So we notice, like, if we take alpha as 1, it fails because this is 12 over 5. It's rational. So alpha equals 1. We know that z see, this is 12 over 5. So that fails. 2. That means x equals 23 over 5. Well, that fails. If we take 3, we have x equals 34 over 5. Fails. We notice the pattern right here. So we have 2, 3, 4, 1, 2, 3. So you notice it's going to be 4. So this just means x equals 1, 2, 3, 4 plus 1 is 5, and then 5. So basically this satisfies because that's 9. So this is check. So therefore alpha equals 4. All right. So we solve for x, essentially. So x is 45 divided by 5, which is 9. So remember, x is an element of, this is this is a set notation, but we already know that this equals, the initial term is 9. So it's an element of, the initial term is 9, and then we have 9, so this is an infinite extension. We have 9 plus 11 times 1, 9 plus 11 times 2, dot, 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 9 plus 11n, where n goes to infinity. So right here, like, let's say now, so now we know that P9, this is where x is 9, is 6 times 9 plus 1 is 55, or 54 plus 1 is 55. And we know 55 divided by 11 equals 5. So basically, A divides Px, or P9, or in this case 11 divides P9. So this is all the cases. We know that this is a divisor. We have the divisor A divides P9, but then we also have, notice that this is okay, so we have P9 plus 11. So we take P9 plus 11, P20, oops, so we have P20 equals 6 times 20 plus 1 equals 121. And we also know 11 divides 121 because 121 equals 11 squared, 11 times 11. So, and then we know if we did P9, we could do P9 plus 11 times 2, which is P of 2231, which is 6 times 31 plus 1. Let's see what this is. It's 180, 187, I believe. So 187. So if we did 11 times, what's this say? 11 times, originally what do we do? 11 times 5, that's plus 6. So we're using that pattern. Let's try 11 times 17. 17, 11, we got 7, 1, 0, 7, 1. This is 187. So that holds true. So given that pattern, we notice you just keep adding 6. We took 11 by 5 initially. Now we're taking 11, 5 plus 6. And we take 11, 5 plus 6 plus 6. And you take 11, 5 plus 6 plus 6 plus 6. And you continue. So essentially, yeah, this is just the algorithm to get the infinite set of non-prime numbers right here that divide P9. So basically, P9 or 9 plus 11 times n. So you start with, this is the initial index, and the index is repeated by a multiple of a, and we can find a divisor. So this takes care of all the non-prime integers of that form. However, from getting from here to solving the Goldbach is really would be really difficult. But yeah, that's just all I have, and I hope you enjoyed it.